Hi, if you want to know how to temperature stabilize your radio, then this is the right video for you. Welcome to TRX Bench. Okay, and let's go right into the video. And if you've seen my last video, so video number 141, you know that we are working on a new repeater station. Last time we tested the transmitter radio together with a fresh aligned duplexer, and now we have here our receiver. And as you already may see, this receiver here has only a normal crystal. I mean, nothing wrong with a normal crystal, but the stability, especially the temperature stability, is often not very good. And so we just want to think about what we can do to stabilize this crystal here, that it will not drift with the temperature. And you know, temperature is really an issue because you know, during winter time it is really cold, or in the summer you have really maybe high temperatures. So you see there is a variety of different environment temperatures, and therefore we need to find a way to simply and easy and cheap stabilize the crystal temperature and thus the drift of this receiver. And of course, this crystal here is the so-called master crystal on which all other frequencies depends. And this master crystal has a frequency of 20.95 megahertz. And that means if we are considering that this is a UHF radio or a UHF receiver, then you may understand that only 1 hertz offset means that the error will be 20 times bigger or greater on UHF, so that means on 450 whatever. So it is very crucial to get this frequency here, first of all, very precise aligned, and therefore you need really accurate frequency counters. But additional to that, we really need to stabilize it, because otherwise it would drift by temperature, and that simply means that we always have a very huge error, what we really don't need. In video 48 we already discussed a very straightforward solution to stabilize crystals. But, well, the issue is we do not have a lot of space in this receiver, so we cannot install, you know, an additional board in here and to do the temperature sensing and what have we. So we really need to find an easy solution what simply fits here into this design, and therefore that what we have done in video 48 would not really fit here into this design. But we have a solution how we can handle it, and you already see we have here PTC thermistors. And oh, what is a PTC thermistor doing? And that is how they look like. And now we need an idea what these little guys are doing. Okay, and PTC stands for positive temperature coefficient, and that means, with other words, this component is increasing its resistor with temperature. Well, and maybe this graph here will already explain all your questions. I mean, it is very easy to understand if this here is resistance, and you see here we have our temperature, okay, and you see with temperature the resistor is going up, right? That means as long the PTC is cold, we have a very high current flow as the resistance is low. So that is basically Ohm's law. Now the temperature is going up, and when the temperature is going up, our resistance is going up, and that means that our current is going down. And this characteristic is very, very helpful here for our needs. And of course, what we can do first, we can test here the so-called 20 or 25 degree C resistance. And that is the start of resistance. And of course, if we then connect this resistor to a voltage, and in our case it is like our radios work with 13.8 volt DC. So that means when we now connect our thermistor to our 13.8 volt, then we will have a current flow. The current which will then flow here through our PTC means that the PTC is getting warmer and warmer and warmer. And when we have seen our graph, we know that with a certain temperature, our resistor will go up. And we know when the resistor goes up, then our current goes down. So that means that somewhere the temperature of this PTC will stabilize. And the really nice thing is that this gets really, let me not call it hot, but it is really warm, maybe around 50 degrees C, and that is definitely enough to finally heat here our crystal. And you may understand that if we really bring it here very close to our crystal, okay, then it will heat the crystal, and when we have a temperature drift due to environment reasons, so day or night or such, then of course our resistor will change, and that means that the PTC will react on the changing temperature, and that subsequently means that the temperature gets adjusted, that finally the crystal temperature will stay in a very small window, and that is exactly what we are looking for. Yeah, and as already said, we can test here our 20 degree C start-off resistor, or whatever we want to call it. So let me test it, and you see it is around 50, it is a little bit jumping, so let me see that I can get it quiet here. So our resistor, our 20-25 degrees C resistor is 55 ohm, and that means that we can calculate our start current which will flow through this PTC. Well, and that is very easy. Again, Ohm's law. And we have 13.8 volt and divided by 55 ohm. So that means our current when we switch it or when we connect it to our 13.8 volt will be 250 milliamps, but it will decrease very, very quickly and will hold, you know, a temperature, and finally it will hold a current which is permanently flowing here through our PTC. Okay, so I have connected here our PTC to our power supply, and let's see if it is possible to see the 250 milliamps, or if it is that fast that our instrument can't really follow. So you see the power supply is set to 13.8 volt, and the maximum current is set to 1 amp. But we know that we do not need 1 amp, so we calculated that this PTC will maximum draw 250 milliamps. So let's see if we can follow it, and then finally we see our final current flow, which will permanently run through our component. So watch now here our amp meter. If we can follow, I switch now the power supply on. And yeah, I guess we have seen it. A very, very short moment. We have seen that there were approximately 200. I have to double check the video, but I think we really were able to see our 200 something milliamps, and you see now it is only 22 milliamps which is flowing here. Now I've lost here a connection which is flowing here through our thermistor, and when I, you know, that was a short, and when I really grab here the thermistor, I can feel that it is getting warm, and the temperature which I can feel here is really enough to heat our crystal, to keep it on a constant temperature. So that is really nice to do it that easy. Okay, and I thought it might be a good idea here to use our little flare and to check here our temperature. I hope that I will be able to get it. It is reflection here as far as I can see it. And when I am able here to meet really the hot spot, and I'm just moving here a little bit, but you may see when I'm able really to meet here the hot spot, we are approximately around 50 degree C. Be careful, it is C, so sorry, I can't directly. Can I convert it? Let me check No, I can't convert it here directly into Fahrenheit, but approximately 50 degree is really a nice temperature to use it as a little oven for our crystals. So you see it is really doing its job quite nicely. I'm doing it not because I'm not really able to be steady enough to meet here exactly our hotspot. All right, but I guess you got the idea. So there is our little PTC, and you see now our current is down to 16 milliamps, and that is really the second advantage, because 16 milliamps is really so low that it doesn't hurt your power supply in the radio. So 16 milliamps is almost nothing, and therefore that is perfect. And I have here freezer spray, so let's simulate that our temperature is varying. So maybe during winter times or night, then the temperature is dropping. So let me put here some freezer spray to our PTC, and let's see what will happening to our current. Okay, so I'm back here to the instrument, and now let me put here a bit of freezer spray down to our component, and you see it is really going up, and that is simulating that the PTC is always trying to keep up it figures, and now you see it's getting more warm and warm, and you see our current is dropping once again, and that means our PTC is really able to follow the different temperatures, and thus it is really able to finally keep here our crystal temperature. Okay, enough theory. Let's go back to hands-on, and let's see how we can get our nice little PTC to our crystal here, that we can heat it like a crystal oven. Right, so the first I've bended here my component a little bit, so that I can get it down here like so, and I try to solder it here onto the crystal, because then we really have the best possible thermal connection between the crystal and our thermistor, and that is what we need to really get the heat over. Yeah, let's see how that works out when I solder it down here to the crystal. And of course, before we get here any solder on our crystal, we need to carefully sand it a little bit, that it is clean, and will take our solder, and you know, that really needs to be done very, very carefully, that you not destroy anything else. But you see already that it is now clean, so the surface is ready to get new, or not new, solder that we can get here our PTC to it. And of course, additional to that, we have to blow out now any residue. So in a second my compressor will get up. Alright, and the next step really is now to thin it here a little bit. So let's see how it works out, and yeah, you see that works perfect, so no problem. We have already a nice amount of solder here on our crystal, and that is exactly what we need, and yeah, we can go ahead. And of course we have to do exactly here the same with our PTC, so I have sanded the surface as well, and yeah, let's see if we can get here a bit solder on it as well. We do not really need too much, just a little bit like so, and that is already fine. Yeah, you see it is just a little bit, really not too much. Okay, so let's see if we can get it here managed around the camera. So normally it should not be too hard, but well, you never know. So let's see that we really get a nice connection, and it looks good on the first glance. So I have to double check it, but basically to me it looks like that we were really able to attach it here to our crystal very nicely. So that is, yeah, very good, very nice. Yeah, and you see I'm already proceeding here. So I'm connecting here our wires to our thermistor, that yeah, we can connect it, wire here our cables to our supply voltage, because we know already that we need our 13.8 volt, and yeah, that is what we are going to do here. Okay, so far so good. So I've already here connected our ground to ground. I mean, it doesn't matter with our thermistor, but anyways, and I still have not connected here my plus, because I just want to check if we still have our oscillation on this circuit. And yeah, circuit is connected to our supply voltage, and well, additional information is that I put here some isolation hot glue to our crystal, so, or better to our thermistor, that the both contacts cannot really get in contact. So I just want to see if we still have our main frequency or master frequency working, and yeah, let's do that first. Okay, so let me try to get here down to our test point, which is, as always, a little bit tricky. But yeah, here we are. And you may see in the right upper corner our frequency, so it is 20 point something. I mean, to measure this frequency, of course, we need we definitely need a frequency counter, as you know, we need accuracy, but I just wanted to see if it is working. And yeah, so that was our first test. Our master oscillator is working, and that is a good sign, so we can go ahead. Okay, so my next test will be when I pick here our master oscillator frequency, and we just display this frequency on our frequency counter. Then I just want to grab here our crystal with my hands, and of course our human body temperature is higher than what we have here in the lab. So I'm simply interested what will be the temperature drift by simply touching the crystal with my fingers. Okay, and you see I'm down here at our test point, and you see we have a error of 3 point something hertz, which is quite good. I mean, I have here 23 degrees C in the lab. And now let me simply touch, as discussed before, the crystal with my fingers, which I'm doing right now. And you see, only with my fingers, yeah, suddenly we are 10 and more hertz off. And yeah, that is really enormous. So let me see. Let's see if I can get it in here. So I'm testing really down here at our circuit. So really no fake. And really, if I'm only touching it with my fingers, and you see suddenly a frequency error, and even in that short time, you may imagine that it is really a problem if you have this unit up and running, and all the different environment temperature will always lead to an error. And remember, we discussed it earlier. If we have only 1 hertz error here with our master reference, then that means our frequency on the 70 centimeter bands will 20 times off. And that really is a huge amount. So we really need to get it as best as possible stabilized. Okay, and that now means we have to connect here our red wire to plus 12 volt, and then of course we switch the unit on, and then we leave here our thermistor burn in, or our circuit, we let it burn in, maybe half an hour or an hour or whatever. And then again we test our frequency, and then with the heated crystal we will then adjust our crystal frequency exactly to our 20.950 megahertz, and then we can be sure that in operation the temperature around our crystal will almost be the same, and the temperature drift we have to expect will be much lower than what we have seen by now. Alright, so far all is done. So now our thermistor is completely connected to our power supply, or to our power input, whatever you want to call it here. Yeah, I have fixed here our crystal a little bit with hot glue, that it is not so loose, and the same I've done here to our wires which are going along our housing. And so that is what we have needed to do. And next step, as I already said, we let it burn in, and then let's see what the temperature arrow will be after, I don't know, half an hour, hour, or whatever. Okay, so it is approximately 1 hour later, and you see it is still closed here, our receiver module. And interesting might be that we can see here our current consumption, which is 78 milliamps, and well, our module itself is consuming approximately 60 milliamps. So we have additional 18 milliamps, and that is telling me that we have obviously the highest resistor of our thermistor, because we have a good temperature. So we have tested it before, and we have seen that we have then approximately 50 degrees C, and just here from our figures we can say that it must be around that temperature. Okay, and when I now take off the lid here, alright, you see our circuit is still working, and yeah, you can trust me. So we really have a very nice and warm crystal, exactly how we like it. So that means that it is really working fine. And yeah, interesting enough, you see that simply here, when I'm touching the crystal right now, you see that our milliamps are increasing, and that is a clear sign that even my body temperature, which is now lower than our crystal temperature, is simply reducing our temperature, and our PTC or thermistor is trying to compensate it by letting more current flow through our circuit. So that is clearly showing that it is adjusting here our crystal. And of course we are now curious to see what will be now our frequency. So we have seen that it was very close by room temperature, and now let's see, when I get a good contact here, let's see what our frequency is right now. And you see that we are approximately 100 hertz off, and that is enormous, and therefore it was absolutely the right way to let it burn in and let it get on temperature, so that we now with our hot crystal or warm crystal or whatever, we can align it that finally when this module is in use, it will always go back to this working temperature, and then we can be sure that our master frequency is on the right setting. On the circuit we have here our pot, and with this pot we can align our crystal frequency to 20.950 megahertz, and now with our warm crystal we will do this alignment that we can sure that everything is just fine. Okay, so that is our start frequency, and now let's see if we are able to get it where we need it. And you see I'm already turning, and that was far too much, because it is always touchy, and it always needs a while to settle down. So as I very often told you, you really need patience to do alignments like this. So to hurry doesn't make any sense. So you always need to let it settle a little bit, that we have a clear reading. But you see we are getting closer and closer. And you see we are really so close. I mean, this digit here is for 1 hertz, so that are millihertz, which is incredible low. And yeah, so the rest here is always the most challenging point. So you see I'm again over. So let me do it off frequency, and you got the idea, and if I have it aligned, I get back to you and show you the final result. Okay, and that is now the best I can achieve here. So it is really difficult enough to keep it here in a good range. I mean, this is not an oven controlled oscillator, and it is not TCXO. So at the end it is only a crystal which we have now temperature stabilized just a little bit. So that is better than the crystal for its own, okay? And even it is working just fine. You cannot compare it with an OCXO or TCXO, but it is really a very good compromise to get really a crystal under control. And that really makes sense, and you finally see that it was easy to handle. So this component is approximately $5 or so, and it is yeah, I believe even a less experienced technician can handle it. So it is really no problem, and it will improve your system quite a lot. Alright, so that it is for today. So now the new repeater really can go up and working. Yeah, I have to do here a final alignment here on our bandpass filter. So that is the final job I will do, or it is not alignment. I will check if it is all still working. But finally, that's it. And I hope that was nice additional information for you all, because you can do that by your own. That is really easy. Okay, thanks for watching, and catch you next time. Bye.